Hello and welcome to the 1.06 Errors in the Laboratory and Percent Error Screencast. I'm Mrs. Willie and let's get started. Our objectives today are to learn how to collect data and make measurements with accuracy and precision. Accuracy is the degree of closeness of a measurement to the actual or true value. The closer you are to that true value, the more accurate the measurement. So a very good example of this would be if I was playing darts, the bullseye is worth the most points. So that is where I am trying to get every time I have a turn. So the closest I am to the bullseye, the more accurate I am. Accuracy in measurements refers to the closeness of a measured value to a standard or known value. For example, if in a lab you obtain a mass measurement of 3.2 kilograms for a given substance, but the actual or known mass is 10 kilograms, then your measurement is not accurate. Precision, also called reproducibility or repeatability, is the degree to which repeated measurements under unchanged conditions show the same results, or how many decimal places the measurement can be reported to. So back to our dart game example. This time, if you see our picture, the person did not hit the bullseye. They hit outside the bullseye, so their throws were not accurate. But they had 4 throws and they were all very close together. So their throws were precise, but were not accurate. Precision refers to the closeness of 2 or more measurements to each other. So using the previous example, if you mass a given substance 5 times and get 3.2 kilograms each, then your measurement is very precise. Or if you remass the given substance on a balance that measures and reports to 2 decimal places 5 times, 3.20 kilograms is your result. Precision is independent of accuracy. So we use precision in our measurements in chemistry a lot when we are dealing with graduated cylinders or burettes or volumetric flasks. Thermometers, a lot of glassware besides balances. So on glassware or rulers, you read all clearly marked digits and estimate one more place beyond that. All these digits are sig figs. So if I'm trying to read the measurement off of this example, I can see that I know 35 and I know 40. So this must be 36, 37, 38, 39. So that means that this piece of glassware is precise to 1 milliliter. So if I'm looking at this and I know this is 36 and this is 37, I know the 36 and the 37. My unknown would be the half. So I would report this as 36.5 milliliters or 36.5 milliliters. You cannot read beyond the capacity of the glassware. A 10 milliliter graduated cylinder can only measure up to 10 milliliters. And you read from the bottom of the meniscus. So a few more examples. Again, I'm looking at the intervals or the lines on my glassware. Here, I have a 6 and a 7, so this must be 6.1, 0.2, 0.3, 0.4, 0.5, 0.6. So I know that 6.6 are certain. One more, I go one more uncertain digit, so that would be 6.60 milliliters. Here, I have a burette. So these are to use where you're dropping liquid out of the bottom. So unlike a graduated cylinder where you read from the bottom up, I read from the top down. So I know 27, I know 28, 27.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. So I know 27.7. This would then be 27.8. This is 27.75 milliliters. On our last example, this is the 20, this is the 30. So this is a little tricky. These are full milliliters. So this is going to be a 21, 22, 23, 24, 25. So I know 24, my uncertain digit would be 0, so I would report that as 24.0. So there are two types of laboratory error. The first is systemic or determinate error. It has a definite direction and magnitude and has an assignable cause. Systemic error can theoretically be eliminated by repeating the trial in question while paying special attention to the procedure. So to fix systemic or determinate errors, you fix performance or procedure. Biggest thing is, like we talked about last time, how do I read my glassware? Make sure I am reading my glassware and taking my measurements properly. Random is the other type of error, or indeterminate, arises from statistical uncertainties in a measurement or from errors that are out of your direct control. Random error can be minimized but cannot be eliminated. A lot of this happens in the lab. I don't have control over the temperature, the pressure, the humidity, the airflow in the room. So these fluctuations are beyond my control most of the time in a high school classroom. These would be considered random errors because I can't fix them. The only way to try and lessen the amount of random error in your laboratory data is to take more trials, and that will help lower the statistical uncertainties. The following are not errors. Your lab partners, people are not errors. Punching calculator buttons wrongly, writing data down wrongly, anything that falls in the area of calculator error or human error are mistakes, but they are not scientific errors. So let's do an example. Your lab partner leaves the glassware wet in between trials. Let's think. Is this a procedural problem that I would be able to fix if I went back and redid my trial? Or is this something that is beyond my control? I'm going to say this is something that could be fixed if I were to go back and redo that trial. So this is systemic. So in the lab, we report our level of error through the percent error formula. To determine the amount of error, systemic or random, we use a calculation called percent error. It expresses as a percentage the difference between an approximate, experimental, or measured value and an exact, actual, true, or known value. So the formula is percent error is equal to the true value minus the experimental value divided by the true value times 100. Usually percent error is expressed as an absolute value, which means it would not have a negative in front of it if it gave you a negative answer. Always, always, always show the substitution of the values into the equation on your paper before stating the final answer, and always, always, always place the correct unit after your answer. You measure the boiling point of ethyl alcohol to be 75.0 degrees Celsius, but the actual boiling point is 80.0 degrees Celsius. What is the percent error? So I fill in the actual boiling point, so the actual or true value minus the measured value divided by the true value gave me 0.0625. I will multiply by 100 because I want to put it into a percentage to give me 6.25%. And you will learn this in the next screencast. But because I had subtraction, I will have to go by decimal places, so I would round my answer to 6.3%. Thank you for watching. See you next time.